Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on computer architecture. We have covered some of the basics of computer architecture. We have looked at instruction sets, we have looked at types and addressing modes, and we have now been looking at arithmetic unit. And in looking at arithmetic unit, we have been looking at adders and subtractors, how we deal with overflow when we do addition, subtraction, so on. We have also started looking at multiplication. So, we will just take a brief look at what we have already seen in multiplication and look at other techniques for multiplication today. So, what are we going to do today? Basically it is this, we will look at multiplication. What we have already seen actually is what we call as parallel multiplier. Today we will look at sequential multiplication, and we will also look at division, and if time permits we will also look at floating point operations. So, let us look at multiplication first, just a brief overview of what we do in terms of multiplication. When we look at multiplication of unsigned numbers, we have the multiplicand and the multiplier. So, remember what we do in the normal usual multiplication that we do. So, we take each bit of the multiplier, multiply the multiplicand by that bit. If it is a 1, you have the same number. If it is a 0, it is all zeros. It is shifted and then we add. Basically, we can look at unsigned multiplication as addition of shifted versions of the multiplicand. That is what we see over here. You have the multiplicand, there are shifted versions of this multiplicand which are added. And point to note is that the product of two n-bit numbers is at most a 2 n-bit number. Now, when we do a parallel multiplication, we construct what is called as a multiplication cell, which takes care of what needs to be done for each bit. That is, if we look at this picture here, we know that we need to, if you look at what is happening for instance here in this particular column, you know that there is, you will have first a bit which comes from the previous step which is added to this number, and that may give rise to a carry and a sum. So, we need something which will do a multiplication. Basically the multiplication essentially is an AND operation and the addition of the previous partial product that is created. So, this is what we have here. So, for every bit what we therefore have is a bit of the incoming partial product which comes from the top row, and then you have the actual this ith multiplier bit which is ANDed with the multiplicand bit. So, that gives you the multiplied number, and then this is added with the previous carry in, and you get the bit of the outgoing partial product and you have the carry which is sent out. Now, this carry out will go as the input to the next stage. So, by constructing such multiplication cells and arranging them like this in this order, and by passing the correct multiplicands and the multipliers to these rows and columns, we come up with the complete product, right. So, this is what we have seen in terms of what is called as a combinational array multiplier. Now, this combinational array multiplier, it has certain advantages and certain disadvantages. The advantage is of course that it is a very fast multiplication because it is just a combinational logic that is used. But if you look at the disadvantages, the disadvantage is that it has a very high gate count for multiplying numbers, especially when you look at large numbers, that is for practically we will be looking at least 32-bit or 64-bit numbers being multiplied. It requires a large gate count because remember, for every bit that you have an AND gate and we have an adder that needs to be put in place. So, what happens therefore is you will have a large number of gates that are used when you go in for this kind of a combinational array multiplier. So, what we try to do therefore is, how can I reduce the number of gates that are used for multiplication? If you look at it from that point of view, we can look at a technique where we will kind of combine some sequential technique and use less amount of combinational logic and come up with a multiplier which will do the same job with less number of gates. Of course, this sequential multiplier may take a little longer time when compared to the combinational multiplier. So, we basically make a choice. If you want a very fast multiplier and you do not mind spending on the number of gates that you have, you go for a combinational array multiplier. If you do not want to have so many gates, we would like to optimize on the number of gates, and we do not mind compromising on the time taken, then we go for a sequential multiplier. So, we will now take a look at how a sequential multiplier basically works. Again, remember, the sequential multiplication is essentially the same process that we do when we do manual multiplication. Okay. So, remember the rule for generating these partial products that we have. So, if the ith bit of the multiplier is 1, we add the appropriately shifted multiplicand to the current partial product. So you can look at it like this. First I take this first bit 1 and then I have 1101 over here, right. So if it is a 1, you are adding the multiplicand as it is. In the next bit also is a 1, so you add this multiplicand to this partial product that we already have, right, and the shifted version of this is being added over here. Okay, so this is what we do. Now what we need to look at here is the way this shifting and the addition gets done. Okay, so if you look at it carefully, what is happening here, the multiplicand we can see is shifted left when added to the partial product. That is how we are used to doing the manual multiplication. However, you can look at it a little differently. That is, instead of adding a left shifted multiplicand to an unshifted partial product, you can instead add an unshifted multiplicand to a right shifted partial product. Okay, so this is what I am trying to say over here. So look at this here. So this is my partial product 1010. Let's say this is the multiplicand that I have. Let's say that's also another 1010. Normally what would I do? I will shift this left and add it to this partial product. Instead what I am saying is, look at it like this. Now if I keep this constant, right, if I don't shift it, I assume that this is the actual position, I can look at the partial product as being shifted right and added to this, right. So just a relative positioning that we have. Either I can say this is shifted left or I can say this is shifted right. Okay. So the moment we say that this is shifted right and we keep this position constant, we find that it becomes easier to implement this kind of a multiplication process. So instead of doing the normal shift left operation, we will be looking at doing a shift right operation of the partial product. Okay. So this is the idea that is used in sequential multiplication. So the circuit therefore that we have for doing the sequential multiplication is as follows. So remember what I need to do, we basically need an n bit adder, because at every stage I am going to be adding this n bit number, which is the multiplicand with the partial product. Okay. So this is basically what we have for the sequential multiplier. Look at what we have here. Alright. So I will use one register here, okay, which will be let's say this is where my final part of my final product will be. Okay. So let's say I call this a register A, okay, which is initially 0. Okay, this value is initially 0. So remember, this is my partial product. Initially my partial product is going to be 0. So therefore this is first filled with zeros. Then I have another n bit register where I store the multiplier. Okay, multiplier Q is stored over here. And then I have the multiplicand M, which is stored in another register here. Okay, so this is what we have. And then there is a control sequencer which will determine whether you need to add or not, depending on whether the multiplier bit is 1 or a 0. Remember our multiplication rule. If the multiplier bit is a 1, then we will be doing an addition. If the multiplier bit is a 0, remember only zeros are being added, which is as good as saying no addition is being done, or you can say I am adding zeros to it. What is being given here? So whether I give zeros or whether I give the multiplicand as the input. Here I have a multiplexer which will choose between these two. And this multiplexer will be controlled by the control sequencer depending on the multiplier bit which is coming in from here. Okay, so either 0 or the multiplicand will go over here and the partial product will come from this register, and this n bit adder will add that in the value there, that is these two values will be added, and that will be stored back as the partial product here to be used for the next step. This is for the first step. In the next step, what do? Remember, we are going to shift the partial product right and add the unshifted multiplicand. So let's say we started with the first bit. The first bit of the multiplier, let's say, was a 1. What would we have done? We would have looked at this 1 here. Based on that, we know that the multiplicand has to be added to this partial product, and that value would have been stored here in this A register which stores the partial product. Now what we do is, next step is you will shift the whole thing right. So when I shift right, what will happen? Look at what I have here. The last bit of this partial product, which actually is my final answer as such, that gets shifted into this register here, into this bit here, which is the part of the multiplier bit. Okay, and so you store this value here, and everything else here is shifted right. So when you shift the whole thing right, remember Q1, which was in the position before this, will now come to this position, and so that is the bit that we need to examine now for determining whether the multiplication needs to be done or not. So based on that bit, again the control sequencer will determine whether an addition needs to be done with the multiplicand or whether a 0 needs to be shifted in. So again the same process will take place. Now this same process will take place n times. So you will have n shift right and then add operations At the end of this n shift right and add operations, you will find that the partial product, which is a 2n bit number, will be available in both these two registers put together. That is, A and Q together will hold the final product for you. So we will take a look at this with an example so that you will know exactly what is going into each of these registers. Okay, so remember this picture, okay, and we will put numbers into these registers here and see how the whole thing works. So let's look at this example. Initially, let's look at the registers that we have. A, remember this is our A register which will store the partial product. M is the register which has the multiplicand. Q is our multiplier. Okay, so this is what we have. Now, what is the first step? Remember, you have in the A value is initially filled with zeros. Now, C is the carry that will be generated, which is also 0 initially. It's all cleared initially. And we first look at what is the first step? We'll first look at this first bit over here. This is a 1. So, what do I need to do? I need to do an add. Okay, so 0 0 0 0 is what the value I have in A. I add 1 1 0 1 to this. So, the value I have here in this A register now will become 1 1 0 1. Okay, so I have added this and stored it in register A. Okay, these two are added and stored in register A. Now, the next step that I need to do is a shift operation. So, look at what happens when I shift this. So, this 1 1 0 1 including the C here. So, this 0 will come in over here, okay, and then this 1 will shift here, this 1 will shift here, this 0 will shift here. This 1 you can see is going to shift into the next position. So, which is why you have a 1 over here. This 1 0 1 1 again is similarly shifted right, okay. So, 1 has come over here, 0 has come over here, this 1 has come over here, okay. So, now we have the second least significant bit in the least significant bit position. So, for the next step, the second cycle, we need to examine this bit. So, this bit is a 1. So, we do an add operation again. So, what do I add now? We have the shifted partial product here, remember 0 1 1 0. So, the shifted partial product is added with the multiplicand 1 1 0 1. Okay. So, M and this shifted partial product are added. So, if I add 1 1 0 with 0 1 1 0, I will get a value of 0 0 1 1 with a carry of 1. Remember, I am just doing this simple addition. 1 plus 0 will give me 1, 1 plus 0 is 1, 1 plus 1 will give me 1 0. So, I have a carry here, 1 plus 1 0 and a 1. So, you have 1 0 0 1 1. This is the new partial product now. So, now what do we do? Now we have done the addition. So, next step is a shift operation. So, similarly now let us do a right shift. So, when I do a right shift, look at what is happening here. Similarly as we did in the previous step, this 1 will come over here, 0 comes here, 0 comes here, 1 gets shifted here, this one gets shifted to the Q register, and then in the Q register similarly all these things are shifted out, 1 here and the 0 gets shifted here. Now, for the next step, now we need to examine the least significant bit here, which is 0. Okay, now 0 is, remember, this is our third bit of our multiplier that has come now to the least significant bit position. So, in this position I look at the 0. So, 0 means I do not need to do an add. Okay, so no add is the decision that is taken. Okay, so which means the same value which is there in the A register will remain as it is, because it's like saying no add or adding zeros, both are equivalent, right. So, you just have the same information here, and remember the next step I need to do a shift operation. So, there is no add, so the same value remains here, and then the next step I do a shift operation. So, now this 1 0 0 1 becomes 0 1 0 0, this 1 gets shifted here, these two ones get shifted to the next positions, right. So, you get 1 1 1. The last step, now this is a 1, therefore I will do an add operation. So, to the 0 1 0 0 that I have here, I will add the multiplicand 1 1 0 1, which results in 1 0 0 0 1 here. Okay, this is the new partial product now. Okay, now this new partial product has to again to be shifted right to complete the last step. So, you shift this right, then you will have a value of 1 0 0 0 1 1 1 1. This becomes the final product that we have. So, if you multiply 1 1 0 1 with 1 0 1 1, this will be the final product that is produced. Okay. So, this is how the sequential multiplication mechanism works. What we have seen now is for a unsigned multiplication. So, what we need to look at therefore is, does this mechanism change if I do signed multiplication, or is there some trick that I can do in order to use the same kind of multiplication technique for signed multiplication as well. That is what we will look at next. Take a short break and come back and look at how signed multiplication is carried out. Welcome back after the break. So, we just looked at how sequential multiplication is carried out. Now, let us see how the same kind of multiplication can be used for signed multiplication, or we will see whether the same thing can be used for sign multiplication as well, or if any modification is required. So look at what we are doing when we do sign multiplication. So normally when we talk of signed numbers, we talk about using 2's complement of the signed operands, right. So when you have 2's complement signed operands, okay, look at how the multiplication actually works. That is, let us say I am having minus 13 multiplied with plus 11. Remember, the multiplicand here is negative, but the multiplier still I am treating it as a positive number. Okay. So let us look at what is happening here, right. So you have 10011, right, which is my minus 13. Remember, now I have a 5-bit number compared to a 4-bit number, because now I am treating it as a signed number. So I have one more bit for the sign bit. So this is my minus 13 in 2's complement representation, and this is my plus 11 again in 2's complement representation. Okay. So now look at what we do in this when we do the addition, right, I mean the multiplication. So first step is, this is a 1, therefore 10011 will be my partial product. Now in the next step, what I will do is, before I do the addition of the partial product with the next number, since this most significant bit here, which denotes a sign bit, is a 1, when I do the addition, I will extend the sign bit for all the positions here before I will do the addition. Okay. So the sign extension is something that we need to do whenever we are dealing with negative numbers. Okay. So because this bit is a 1, and remember that the next bit, when I am adding a shifted partial product over here, right, next step is what? Next step is again 10011 that needs to be added. That is, the shifted multiplicand is being added here. When I shift this, if I had not done a sign extension here and this was a 0, remember this will look as if this is a positive number that is being added, whereas my partial product here itself is a negative number, because minus 13 is the value that I have here. So when I am treating minus 13 as a 6-bit number, remember that I will have to put 1s in all these places in order to treat it as a negative number. So whenever we come across a negative number here, all we need to remember is that we need to do a sign extension. So if it is a 1, the entire thing will be shifted with, will be filled with 1s. That is, when I shift it left, I have to remember that whatever is the most significant bit, that has to be copied into the shift in the left shifted position. So if the value is a 0, when I shift it left, it will be all zeros. Okay, if it is a 1, it is again all ones. So this is the change that I need to do when I am dealing with sign numbers. Okay. So if you remember that, and remember that this sign extension has to be done whenever we deal with negative numbers, you will see that the same technique that we used earlier will work wonderfully for sign multiplication as well. Okay. So you can see that when you do this addition, this is the answer that you will get. You will get 110, 111, 0001, which is basically minus 143. Again remember, this is the 2's complement representation of this number, okay, which is why you will find that the most significant bit is a 1, indicating that it is a negative number. So using this sign extension of the negative multiplicand, we can see that the same mechanism that we used earlier will work here also. Now this was good when we had a multiplicand being negative. Now what if the multiplier is a negative? Okay. So what do we do if the multiplier is negative? A straightforward solution is to form the 2's complement of both the multiplier and the multiplicand and proceed as in the case of a positive multiplier, because remember this is also negative, that is also negative. So if you take the 2's complement of both and multiply it, anyway it will be 2 positive numbers being multiplied. So you can treat it as 2 positive multipliers being multiplied together. So just treat it as, just take the 2's complement of the multiplier and the multiplicand and proceed as in the case of a positive multiplier. That is what we need to do when you are doing signed multipliers, that is when the multiplier is also negative. Okay. Of course, this is possible because we know that complementation of both operands does not change the value of the sign of the product. So that is simple. So essentially what we are doing is we are always making sure that the multiplier is positive, so that when we do this kind of a signed multiplication that we do over here, since the multiplier is kept positive and we just do a sign extension for the multiplicand, the whole thing will work correctly. So remember just this, when I do signed multiplication, when I am dealing with signed numbers, I need to make sure that I do sign extension before I do the addition of the partial products. That is all that we need to remember. Okay. So if you do that, you will find that the sign multiplication works, whether the multiplier is positive, multiplicand is positive, whatever be the case, it will work. Okay. If the multiplier is a negative number, then remember that we take the 2's complement of both the numbers, both the multiplicand and the multiplier. So if you take the 2's complement of both the numbers, you are not changing the sign. That is the trick that we use in order to do sign multiplication using the same sequential multiplier circuit. Of course, with sign extension feature being provided for doing the shift operations. Okay, this is what we do. When we talk about doing shift operations with the sign operation, it is essentially what we call as the arithmetic shift. Remember that when we do a shift right and we say it's an arithmetic shift, we take into account the sign of the number as well. Okay, so if it is a 1 and we do a shift, we have to remember that also a 1 will get shifted, right, along with the will come in from the left. Okay, that is what we need to remember. Now what we will look at is another technique which is called the Booth's algorithm, which was introduced by Booth. It's called as a Booth's technique. Now this technique we find works well for both negative and positive multipliers without worrying about whether I need to check and change the number to its 2's complement representation or not. So what we do in Booth's algorithm is we basically try to improve the efficiency of this entire multiplication technique. What we are doing in Booth's algorithm is basically the following. There are two important aspects to remember about the Booth's algorithm. One is that you don't have to worry about whether the multiplier or multiplicand is positive or negative, and you can work with the same kind of using the same kind of circuitry. That is one thing. Second thing about the Booth's algorithm that you need to understand is that it is an efficient technique. That is, it tries to reduce the number of additions that we need to do. Remember, if let's say for instance we had a multiplier which is all ones. If you have a multiplier which is all ones, what you would actually be doing is, since every bit is a 1, you have to do an addition operation for every bit, and there will be a shift operation that will anyway be there. Okay? But if you had more number of zeros in your multiplier, then you will find that the addition operations are less, there are more number of shift operations. Now normally we know that addition is a more time consuming operation than just a shift operation. So if I can reduce the number of additions, I know that I can reduce the time taken for multiplication. Now we worry about time taken for multiplication because the sequential algorithm is a time consuming algorithm compared to the parallel multiplier algorithm. These are the ideas with which Booth's algorithm has been formulated. So remember two things. One is we want to make it more efficient, and second thing is that it should work for easily and well for both signed and unsigned numbers. Okay. So let's look at what we do in the Booth's technique. So we have this multiplication that we are showing here. This is again to basically point out the motivation for the Booth's algorithm. So look at how many appropriately shifted versions of the multiplicand are added in the standard procedure. So let's say I have this number 0, 1, 0, 1, 1, 0, 1, and I have this 0, 0, 1, 1, 1, 1, 0 as the multiplier which is used for the multiplication. Now you can see that the first partial product is all zeros. Next one is the number as it is the multiplicand, again multiplicand, at least there are 4 times that this multiplicand is being added, and then shifted and added with the other zeros over here. So depending on the number of ones I have, as I said, you will have that many number of additions that need to be performed. Rest of them can be just treated as shift operations. So what we are trying to do here in Booth's algorithm is see if we can represent this number 0, 0, 1, 1, 1, 0 that we have here, okay, differently. Okay, what do I mean by differently? I can look at it as the 0, 0, 1, 1, 1, 0 can be written as 1, 0, 0, 0, 0, 0 minus 0, 0, 0, 0, 1, 0. So look at what I mean by doing this. So this entire number here is treated as difference of two different numbers. Okay, this number here is 0, 1, 0, 0, 0, 0. What is this? Basically all I am saying is I can look at 1, 1, 1, 1, 0 as 1, 0, 0, 0, 0, 0 minus 0, 0, 0, 0, 1, 0. If I subtract this value from this value, I will get this number. This basic subtraction, right? If you remember to use this kind of a technique, let's see how it will help in terms of our multiplication. So what I am saying therefore is this. So this number that I have here, I am going to represent it slightly differently. How am I going to represent it? I am going to represent it as 1, 0, 0, 0, right? 1, 0, 0, 0, and now I have a minus 1 over here. So I write this as minus 1 followed by 0. There is this number here that it is 1, 0, 0, 0 minus this number. I am writing this minus 0, 0, 0, 1, 0 as 0, 0, 0, 0, and this 1 is substituted with a minus 1 over here. I represent it like this. So we are going for a slightly different representation here. This can be looked at as a mixed sign representation. That is, you have numbers in this which are not just 0 and 1, but you have 0, 1 and minus 1. Okay. So if I represent my number like this, okay, look at this is my number now. So this is my multiplier. Instead of writing 0, 0, 1, 1, 1, 1, 0, you see that I am writing it as 0 plus 1, 0, 0, 0, minus 1 and 0. The moment I write it in this manner, look at how my multiplication will change now. So what will happen to my multiplication now? First bit is a 0, so it's all zeros, my first partial product. The next bit now is a minus 1. So when I multiply minus 1 with this, now minus 1, remember, it's like multiplying this whole thing with a minus 1 would mean I am taking the 2's complement of this multiplicand. So take the 2's complement of the multiplicand, that is my minus 1 into this value. Okay, what is minus 1 into a some number? It is the negative of that number. So negative of that number is nothing but the 2's complement of that number. So you take, whenever you come across a minus 1, therefore take the 2's complement of the multiplicand, put it over here. Of course, remember, whenever we take 2's complement, we will also do the sign extension. So with the sign extension, you put the 2's complement over here. Next bit is a 0, so all zeros. Next bit is 0, again all zeros. Next bit is also 0, all zeros. Next bit is a plus 1. So I will now multiply 1 with this number, right? So I will get 1 0 0, 1 0 1 1 0 1, of course extended with zeros. Next bit is a 0, so you multiply that with zeros. Now you add all these partial products, that will give us our final answer. So look at what is the essence of doing this whole thing. What we have done therefore here is, instead of having 4 additions as we had in the previous step with this multiplier, we have now reduced the number of additions to just 2, right? There is one addition with the 2's complement number and one addition with the straight number. So what is it we have achieved? We have reduced the number of additions that need to be done. Okay, this will work very well whenever we have this kind of a series of ones that are coming together. This is the idea that is used in Booth's algorithm. And since we deal with both positive and negative numbers in our representation itself, if it is a negative number also, we do not have to do anything. The moment you have represented it in this manner, right, you can automatically just take either the 2's complement of the number if it is a negative number, if it is minus 1, and if it is plus 1, then you take the number as it is and you will add it. Okay, so this is what we do. So look at what we get when we do this. So the question therefore is, how do I convert a given number into this Booth's representation, this Booth's recoding that we talk about. Okay, so what we do here is, if I have a number like this is my series of numbers that I have, you keep coming from the right. Whenever there is a shift from 0 to a 1, right, you replace it with the minus 1. For zeros are copied as it is. Whenever I go from 0 to a 1, I replace it with the minus 1, and then following that, whenever I have ones, you just keep putting zeros there. But when I have a 1 to a 0 shift, then I put a plus 1. Okay, again I have a 0 to 1 shift, I put a minus 1. Okay, and then a 1 to a 0 shift, I put a plus 1. 0 to a 1 shift, it becomes minus 1. 1 to 1, it is 0. 1 to 1, it is 0. Right? 1 to 0, if there is a change, again this becomes a plus 1. 0 to 0, no change, so this will be 0. 0 to 1, change, therefore this is minus 1. 1 to 1, no change, so 0. 1 to 0, it will become plus 1. 0 to 1, change, minus 1. 1 to 0, change, plus 1. 0 to 0, no change, 0. So given any number, we should be able to write it in terms of these minus 1s and plus 1s in this manner. Okay, the moment you write it like this in terms of minus 1s and plus 1s, it becomes, you have recoded the number as a Booth's recoded number, and once I have this number as my multiplier, it is fine, right? Now if it is minus 1, I will be adding the 2's complement of the multiplicand. If it is a plus 1, I will be doing the actual multiplicand as it is. Okay, this is what we have with the Booth's algorithm. So this is just one quick last example which shows how this Booth's multiplication will work even with the negative multiplier. So we have this number here 0 1 1 0 1 multiplied with 1 1 0 1 0. So this is now recoded as minus 1 plus 1 minus 1 0, right. So remember that recoding that we just talked about. Now you do the multiplication in the normal manner with just remembering to add the 2's complement of the multiplicand whenever we have a minus 1. So here and here, the two places where we have 2's complement number. Add this and this is your final answer, which is actually given as the negative, which comes in the negative representation. With this kind of a Booth's algorithm technique, the sequential multiplication itself is made faster. Of course, this will work very well when we have a large number of ones coming together or large number of zeros coming together. The worst case situation will be when you have plus 1 and minus 1 coming alternating with each other, because remember when you have zeros and ones alternating, because then you will find that you have more number of additions and subtractions being done. So you can kind of choose to use this algorithm efficiently depending on the situation. So to conclude, what we have looked at today basically is how the sequential multiplier works, and with respect to the sequential multiplier we have looked at the basic technique and we have also looked at the Booth's recoding technique. So with these two techniques, you are in a position now to understand how a sequential multiplication in its normal form works and how it can be speeded up using this kind of a Booth's technique. There are of course other improvements on the Booth's recoding technique, where we try to not just do multiplication using one bit of the multiplier, but we also try to do multiplication using two bits of the multiplier. Those are certain advanced techniques that you could look at. Okay, but otherwise this is what we have covered in today's lecture. So questions to understand today's topic. Question number 1, write down the intermediate steps in the following multiplication: 12 into 14. Question number 2, perform the multiplication 3 into minus 3 using the sequential multiplication. Remember, we have a negative multiplier here. Question number 3, how does the Booth's technique help make multiplication faster? Thank you.